Welcome to the Metadex TCG Game Tracker introduction. My name is Chris Ellis, and I'll be walking through the document with you today. So why are we here? Well, fans of trading card games today have many useful tools at their disposal. They have online storefronts, cards, search engines, deck building tools, and endless articles describing specific strategies that they could play for multiple trading card games. However, there is currently a gap in services when it comes to tracking game outcomes at a casual play level. Currently, players who desire to track their win-loss rate must write their game results down on paper or create their own custom tracking spreadsheet. This lack of data infrastructure causes players to make uneducated decisions both during games and also when purchasing new cards. With no central database of game results to reference, players have limited information available when deciding which strategy to invest their hard-earned money in. Currently, due to the state of the industry, players will make these decisions based on the results posted by professional players, which may lead to vastly different outcomes at a casual play level. A software solution to this problem must provide a quick, intuitive, and reliable way to record game results in order to avoid causing extra hassle for players when they're trying to play their favorite games. And it must also store that data in a scalable, filterable database and use it to provide clear visualizations of the stored game results back to the users so they can make educated decisions based on their game history. Such a system should also connect with other services which are already well adopted by the trading card game community, such as deck building tools and popular storefronts, as that will make using this new tool as seamless as possible for new users. So moving on to our mission statement. The Metadex TCG Game Tracker has the main goal of providing a simple way for players of trading card games to record their game results, and then using that data to provide meaningful visualizations back to those users to help them improve their game over time. I'm just going to go briefly over the functional requirements, but not deep into them. So the system must provide user management, such as authentication and login services, creation and deleting of accounts. It must provide a way to record game results. It must maintain data over time and not risk losing the user's recorded game data. The system must provide data visualization and reports, provide deck management so users can track their game results based on different decks which they own, opponent management so they can track game results against specific opponents over time, as well as TCG data handling. There are multiple different trading card games that this system should support, like Pokemon, Yu-Gi-Oh, Magic the Gathering, etc. And so it must be able to handle all the data associated with each of those trading card games. As far as non-functional requirements, the system should be easy to use, very reliable. We don't want the server to be down when the users go to try to enter their game data. That would be loss of data, so not good. It should be performative, so entering game results should be quick, and retrieving and generating visualizations and reports should be also happen in a timely manner. The system should be scalable, so it can scale with growth in user count, as well as scalable in data storage. And the system should be secure. Security is not a top priority for this system, as there is no sensitive user data in the system. However, we do want to protect users' data from unauthorized access and employ secure methods for storing important pieces of data such as user passwords. The system must be maintainable so that we can grow and add new features in the future without incurring a bunch of cost. And it must also be compatible with common operating systems for PCs and mobile phones, as well as the most common web browsers. So, diving into the design, here we have a use case diagram showing the major use cases of the system. We have account management, deck management, so users can add and remove their decks that they have for their games. They can search for cards. We have some supporting use cases, searching cards, importing decks from external deck building sites, managing opponents, managing game results, and then viewing visualizations. There is only one primary actor for the system, which is defined as a casual TCG player, just a normal user. This is a single user facing system, so there just were no other primary actors, but there are a few supporting actors, like the system administrator, who must manage metadata. So if the system administrator decides to add a new trading card game, then they will do that using this use case. And then there are outside services like deck building sites and card search APIs, which support some of these other more specific use cases. Here's the system domain model. The system has users. Users have roles. The users record game results. Game results are the main object of the system. These are what we use to calculate our statistics and visualizations later on. So a game result is very central to the system. A game result is recording a game of a certain trading card game. And trading card games have specific formats, like Magic the Gathering has formats like Commander, Standard, and Modern, for example. Each format has different rules for deck building and rules of play. So we need to record what format they were playing during that game. And then we need to record what deck the user was playing so that we can track that deck's win percentage over time. And then here's where we track opponents. So there's an opponent class, which can be linked to another user, but it does not have to be. And then there is a game opponent class, which is composed of the opponent and the deck type. So this is the strategy of the deck that the opponent was playing in this game. The opponent ID as well as the opponent deck type ID combined together to form a game opponent. So this is a one-time instance of an object that is associated with a game result. And some formats are multiplayer, so they have more than 2 players. And so there can be multiple game opponents per game result, which is why game result has this field called standing. If you come in 3rd place, you can record that. And then from there, the The deck also has cards. So any number of cards, depending on the size of the deck for the format they're playing. And cards belong to a trading card game. So these are the domain classes. Oh yeah, and decks are owned by users. All right, moving on. All right, so into the design class diagram. So because our system is mostly about data management as well as data visualization and report generation, we broke it down into multiple layers to simplify the maintenance and access of all the different types of data, and in order to separate concerns. So the layers are as follows. So there is a request layer, which includes, one second. Let me zoom in on this so you can see it better. So the request layer handles incoming API calls and formats responses before sending them back to clients. This layer contains no core business logic. So it just it hosts APIs, and it uses the next layers down to execute those the business logic, and then formats the response and sends it back. The service layer classes encapsulate business logic. So they handle the core business logic. They are the controller classes for the entire system. And this is where use case functionality is maintained. So that's the service layer. But the service layer does not interact directly with data management. That happens at the data management layer. So these classes handle data retrieval and maintenance operations. They provide functions to save system data to the database, and they return objects back to the service layer in support of business goals. This is very useful because multiple different service layer classes need to access the same types of data, and so they can each rely on the same repository data management layer class in order to achieve those goals. The database entity layer is the final layer. This is where we'll find our classes from the domain model. So users, roles, decks, cards, trading card games, game formats, etc. These entities are the domain-based classes, and are passed around between the above layers to achieve business goals. So they represent the real-world objects and concepts, and they are instantiated by the data management layer classes based on information stored in the system database. Now, to zoom in on that, obviously this is just a very zoomed out version of the domain model, because there are so many, or the design class diagram, because there are so many classes added here in order to promote separation of concerns. So I've got 4 more views to zoom in on those classes. So here is the user management vertical slice of functionality. So the request layer has API facing functions to register, login, update profile, request password resets, and to return user profile information. That uses the user service to achieve those. The business logic, the user service in turn uses the user repository and role repositories to access data in the database that it needs to perform the business layer use case logic. And those user repositories and role repositories, these data management layer classes, will manage user and role classes respectively. And they generate these classes and return them to the user service in order to using the data that they retrieve from the database. So that's user management. This is TCG data management. Very similar setup. There's a deck controller. This is a front-end class hosting all the API endpoints for updating decks and retrieving deck data. That uses the deck service, which also uses the user service to get user information. So for example, if we wanted to get all the decks for our user, the controller would call the deck service. The deck service is going to get the list of decks from the user service and then return that. A list of deck IDs from the user service. And then it would use the deck repository to generate the deck objects, which it would return to the deck controller, which would then format the response to the API call. There's a deck service, a metadata service. So this one handles all trading card game related data, including what games are supported, what formats exist within each game. And then there's a card data service, which handles retrieving and updating card data for each trading card game. And again, repository layer classes that handle data persistence and generation of domain entity objects. All right, moving on to game result management. Very similar setup here. We have a controller class, which uses a service class. The service class, in this case, game results are tied to many other things in the system. So it uses the user service, deck service, and metadata service, as well as the opponent service, which exists over here. And these services in turn use the data management layer services for opponents, game results, game opponents, and opponent deck types in order to manage data persistence and return database entity layer objects. And then finally, we have the analytics management section of the diagram. So here, again, we have a controller class, a service class, and that service class, in this case, reaches out directly to the repository classes to access data so that it can generate reports and visualizations that can be sent back to users upon request. So Let's talk about the design patterns used here. There's a grasp controller pattern. The service layer classes operate as controllers for their respective use case areas. User service covering user-oriented use cases. Same with deck services, metadata service, game result service, and analytics service. They each cover a small slice of user-facing use cases, and so those are the controller classes. There's also a lot of pure fabrication and the single responsibility principle in use here. So the request layer, service layer, and data management layer classes are all pure fabrications. So everything from here down to here, everything above the database entity layer. They are implemented to separate concerns into different classes. This way, each class only has one reason to change. So for example, the card repository data management layer only needs to change if we change the way we're storing card data. And the card data service only needs to change if we change our business logic around card data. This design choice also embraces the dry design principle as it improves code reuse. So all of these classes, because they're split up this way, they can be used by multiple different services. And so we don't need to repeat ourselves very much. And then finally, the grasp creator pattern is being used here in the data management layer. So they really embody the creator pattern for all of the database entity layer classes, because these classes have the ability to connect to the database and obtain all the information needed to instantiate new database entity objects, which are then used by the service layer classes to perform business logic. So these are creator pattern classes. Okay, next I want to go through some sequence diagrams so we can see how the system actually works to achieve user-facing use cases. So first one is the record game result use case. So when a user uses the front end to record a game result, that API call goes to the game result controller, which in turn calls the game result service, passing the game data. This will validate the game metadata, so make sure that the user asks to record a game for a valid trading card game and format pair. If that's wrong, an error response will be sent. It then validates that the user actually owns the deck that they requested to record a game result for, and if that is not true, it will send an error. And then because game results can have multiple opponents, we need to repeat this next section for each game opponent. So we find the opponent or create it if it doesn't exist. And then we find their deck type or create it if it doesn't exist. So this is a strategy that they were playing. And then we do that again for each opponent if there are more than one. We then save the new game result object using the game result repository. And we save all of our game opponent objects and return a response back to the user. So that was record game result. Let's look at creating a deck. So again, the front end sends an API call to this time to the deck controller API layer class. That calls in turn the deck service to create the deck. This then validates the user exists and validates the trading card game, then creates a deck object and saves a new deck object with the deck repository. Okay, and then there's one here for generating some statistics. So this is get matchup stats. This shows the process of checking a user's deck match results against a certain strategy, so a specific opponent deck type. They will send that to the API. The API sends to the service layer, and then the service layer finds the deck, asks the game result repository to find all the game results for the given deck. And then for each game result, it checks to see if the opponent of that game result was using the requested deck type. And if they were, then we append it to a relevant game results list and calculate matchup statistics, pass that back to the API, which formats a response, and it finally gets passed back to the front end. So those are 3 examples of sequence diagrams. Here you can see clearly how all those design classes work together to achieve use case goals. Because Metadec's system is designed to operate in a very stateless manner, all of the state-based information, if there are any states, is stored in the database, and the database is updated every single time a call is made. So, and because like most of the transactions are instantaneous, as in like they do not have follow-on transactions. Most of our classes do not have states. However, the opponent class does have a state because it can either be linked to a user or not linked to a user. So when you first create an opponent class, opponent object, it will be unassigned, and then the user can link a user, and then the opponent class will be assigned to a user. You can then unlink the user, just put it back to unassigned, and if in any case, if it is deleted, then the object is destroyed. So that was the best example I could think of for a state diagram, because we do not really use state in this system by design. Okay, and now here's an example of a activity diagram. That's a little hard to read. Well, guess we're gonna have to deal. So this is the update deck function activity diagram. So the player will send an update deck request with new information about the deck. The deck controller will validate the request, and if the request is valid, it will, well, if it's not valid, it will send an error response back to the user. But if it is valid, it uses the deck service to find, which then uses the user service to find a user, and then uses the deck repository to find the deck by ID. If the user and deck are not valid, then we send another error response. But if they are, we update the deck properties. If deck list data was provided, then we compare the existing deck list to the provided data, identify cards to add, remove, and update, and we use the card data service to perform that action. And if the deck data was not provided, then we skip those steps. And then following that block, we save the deck using the deck repository, and we send a response of success back to the user. So that's how the update deck function works. Okay, moving on to the component diagram. Zoom out a little here. So each of the four main system components, the user manager, TCG data manager, game result manager, and analytics manager, encompass a vertical slice of user-facing functionality, just like our vertical slices on the domain class diagram earlier. These components are then supported by an API gateway component and a database manager component. The API gateway component can perform load balancing and security functions, while the database manager handles data persistence and consistency between the four main service components. The client provides a user interface, and the user manager supports all user account management use cases. TCG data manager serves all TCG data management use cases. Game result manager supports all game result tracking related use cases, and analytics manager supports data visualization and reporting use cases. And then we have the deployment diagram. So our system is deployed into the AWS cloud platform. And the structure follows a microservices design architecture, using an API gateway to support load balancing and containerization to enable scaling. Each service container includes its own database manager to reduce network traffic. This is following the sidecar pattern of microservice design. And finally, a main database node handles maintenance of the primary database and synchronization between all other database instances. I'm recording. Sorry about that. Okay. So yeah, that's the deployment diagram. Finally, we have some skeleton classes defined. They're available in the source folder here. I'll open up some of those so we can look at them. We have one example from each service layer, or each domain class, design class layer. So here's what a game result entity class would look like. A repository. This is the game result repository class. So this has all the data management functions. The game result controller class. So this is an API layer class. It has all the functions to support API endpoints and return responses. And then here we have a service layer example. So this is the user service. It has all the functions to manage user business logic. So like creating user, authenticating, login, password. Or authenticating is login, but profile management, password reset, and finding users by IDs. We also have database table definitions. As an example, there's the game results table. So over here in our README, I have a sample row of what this database table would look like. So we've got a game result ID. This is the primary key of the database. An outcome, overall game outcome, the time of the data recording, some notes. This is user entered data, same as number of turns. The notes are free form, obviously. Did the user go first or not? Because this is actually very significant in trading card games. And then user standing. In this case, they won, so they got first place. But if it was, say, a multiplayer game and they lost second, that would be third place. Or I don't know, if it was a 4-player game and they lost second, they'd be in third place. And so that's useful for multiplayer game formats. And then here we have primary key IDs for the referenced database entity objects. So user, deck, TCG, and format related to this game result. So these IDs can be used to look up the data from those objects in order to do even more detailed data analysis. And the table definition is here. You can see game result ID is the primary key. A few of these items are optional, but some are not. And then there's constraints as well, like these must be foreign keys for user, deck ID, TCG ID, and format ID. All right, so that's the MetaDex trading card game tracker. Once the system is implemented, it'll begin to provide trading card game players with valuable feedback that they didn't have before on how they are performing at their favorite games. It will allow them the hindsight required to make educated deck building and in-game decisions in the future, which is great. So what can we do to build on this once that's done? Well, we'll have a lot of data. We'll be collecting like so much data about what decks people are playing, the cards they put in their decks, matchup statistics. So there's a lot we can do, but here's a few ideas. We could provide recommendations to the users based on other users' results with similar decks. So we could say, hey, this other players playing cards like the ones you're playing also play this card that you're not playing. and they get better results with that. So we can encourage users to change their decks in that way. Another idea is we can add a friends list, so the friends can add each other and share their decks and their decks related game records with their friends. Then also deck version tracking. So as time goes on, players of trading card games do update their decks, and some users may want to track that so they can see if the changes they're making to their decks are helping their win rate or not. We should add that capability to be able to record it, and then also to visualize, show those version changes visually in the resulting record visualizations. And then in the long run, we will, like I was saying, we will have the data to generate a lot of other stats, like a user's most played deck in the last 6 months. So you can tell them what their favorite deck is, even if they don't know what it is. The opponents they play against the most, which could be interesting. Maybe they don't realize they play against this person more than that person, right? And then also there could be macro level data statistics as well. We could see what the most popular decks are, so in a certain game format, which would be really useful because the decks people build are not always the same as the ones they play most often. So we'd be the only place to go for that data. But overall, these additional insights can provide further feedback to users and therefore improve the user experience. And also, maybe we can leverage it to generate some sort of profit from the tool. So thank you for listening to this introduction to the MetaDex TCG game tracker. I appreciate it. Had a lot of fun designing this, and looking forward to get some feedback. Goodbye.